So what I'm going to talk about, I'm going to start out and mostly I'm going to go over, probably spend most of the time actually on the introductory information. And so we're going to talk about the planning, the what-if scenarios, uncertainties, and models in more in general sense. And I'll introduce probabilistic risk assessment, or PRA, and that provides a framework to tie them all together for decision making. Then I'll provide the case study, and we look at kind of two things there, both climate change impacts and land use and land cover change impacts. And finally, wrap up with a few updates that could be done to this study to make it better, and that's the updating the line section. So, planning is making decisions to map future courses of action to achieve objectives. We're looking at decision making for what, how, when, and who. Environmental planning is a subset of regular planning, or planning as applicable, and it's decision making to achieve combined objectives for development, economic development, and sustainability. And you're going to consider environmental, social, political, economic, and governance factors in your decision making. Water resources planning is a further subset of environmental planning, and it has the focused, much more focused objective of reason-based and cost-effective reconciliation of water supply and demand. You'll notice all of these planning descriptors, definitions, include cost, economics, things like that. All right, so planning is decision-making now to map feasible future courses of action. It's fundamentally decision-making in an environment of uncertainty. Uncertainty is just the lack of knowledge. That's the definition of uncertainty. Future is an unknown and inherently uncertain. So with uncertainty, we often talk about two M-member types. There's exact value uncertainty, just what's shown on this slide. And that's, we have a desired value or our target. So we kind of know what we're trying to hit. But there's always some inaccuracy and some imprecision, but we're worried about accuracy and precision. This type of uncertainty is most typically represented with the Gaussian distribution, or the normal distribution, which is shown on the right. And so you can see the mean, which is represented with mu there, is always the center of mass, right? It's the most likely value in this description of likelihood. You also notice that 68% of the values are within 1 plus or minus 1 standard deviation, right? So we're expecting high accuracy, high precision, okay? The other type of uncertainty, or the other end member, is when we have complete unknowns, right? Unknown unknowns. There's no targets, there's no observations. This is traditionally represented with stochastics, which stochastic is just an outcome realization of a random process. If you have multiple stochastics making an ensemble, you have multiple realizations, multiple random realizations from the same underlying random process. In this case, accuracy is undefined. The typical description of likelihood for this type of uncertainty is the uniform distribution. You see the same likelihood for all options. All right. When this type of distribution is applied for decision making with categories or labels instead of real value numbers, the mean is undefined, as is the variance. All right. So when we're dealing with unknown unknowns, time stationarity is an explicit choice by the analyst. You can choose weak stationarity. Weak stationarity just means we have the same target in the past as in the future. Just in the future, we decide to hang the target on another wall for a couple years, and then we move it over to a different wall for the next few years. Right? So it's the same thing is happening, it's just in a slightly different position. When we have true non-stationarity, then you're dealing with more like different worlds. Right? It's a completely different thing you have up there. So we wanted to talk in terms of maybe climate projections. You could say like weak stationarity type Time stationary would be something like using CNIP6 model results. Non-stationary would be if we happen to have a complete reorganization of the global ocean current system. All right. So, what if questions and hypothesis testing. The what if question is the backbone of forecasting and scenario planning. It provides accommodation for future uncertainty. So, hypothesis testing is, of course, the main portion of the scientific method. Experimental design is the science of formal and rigorous hypothesis testing. A what if question is really just the first part of a formal hypothesis. In logic notation, a hypothesis is if P then Q. If P is a what if question, Q is the consequent or answer. So Q is what you plan for or against, if P is the what if question. Planning and what if questions, of course, are widely used in the social sciences, business, economics, finance, and public policy. From this general perspective, understanding the right and wrong ways to use what if analyses save time, money, and leads to actionable results. And the right way to use what if analysis is to vary the things that you know are most important, right? We have future uncertainty, we could possibly have, widely different outcomes. So you might as well just spend your time varying what you know is important. You don't have time and really just lead down the rabbit hole of uncertainty. Oh, sorry. From the physical science perspective, fortunately, when phrasing a what-if question, you have the scientific method. That's what it's all set up to do. The fundamentals of experimental design. Those are all dealing with what-if questions and hypothesis testing. So when you're comparing scenarios or hypotheses, the outcomes or the consequence, especially when you have uncertainty that is significant and may lead to very different types of outcomes, the only way it's really effective to do the comparison is with dollars. Dollars are the universal language of decision making. Costs and benefits are the only way to compare apples and oranges. The other thing dollars provide for is analyzing how and when is an important part of planning. Money costs different, has different costs, inherent costs, depending on when you need to use it, when you need to acquire it. All right, so in terms of numerical or computer model applications, as with uncertainty, we're going to use two sort of end-member descriptions of models to kind of frame the rest of the talk. So on one side, you have design basis modeling, and that's where you have very concrete thresholds and you're looking at specific conditions, you have accuracy, you have precision, you have exact value uncertainty. For planning, in hypothetical what-if scenarios with ubiquitous uncertainty that requires probabilistic analysis. So we're going to have to do probabilistic modeling. We have the unknown unknowns type of uncertainty. We're going to have the possibility for radically different outcomes. It's a whole different type of model. For planning, both the true future and the right answer are unknown. There is no target, right? It's in the future. The only certainty is that a single answer for a single future will always be wrong. All right? So when you're using models in experimental design, and we saw that what-if scenarios, what-if questions are part of hypothesis testing, which immediately leads you to experimental design for how you use your models. So kind of the guiding principle is all models are wrong, but some are useful. And those of you who have invented a numerical method or developed a computer model, a complex computer model from F equals MA applied to control volume and multiple physical cell models, you know that you're going to spend a lot of time on accuracy and precision validation and stability analysis. And all that is, if it's a numerical method, you're going to spend months. If it's a complex computer model, you're going to spend years. After all that time, all you're doing is carving out a postage stamp of solution space where the model is useful. It's usually fairly depressing to see how small that postage stamp is. All right, so experimental design is the key to making useful models. And really you're just considering, does my model provide the consequent or the answer to my what if question? Will my model take in the things I'm going to vary as part of my what if question? That's all it really entails. And the one important thing to always keep in mind is you want to, as part of your experimental design, you always want to figure out how you're going to deal with your outcomes before you run the experiment. What are you going to analyze? How are you going to analyze it? Is your experiment set up to provide that description that you're going to analyze? So, with models combined with uncertainty, there are again kind of two end members. So we have sort of the standard calibration approach, and that's when you have observed forcing, model parameters selected from professional judgment, simulation results compared to observed targets. This is the classic data assimilation framework. I'm sure everybody who's doing modeling now is using data assimilation. That's really just what model calibration is called now. With data assimilation approaches, you always have exact value uncertainty. So you're concerned with accuracy, precision, and you always have the Gaussian distribution setting your error terms. Probabilistic simulation, on the other hand, is completely different. So with probabilistic simulation, you have stochastic forcing. This is the unknowns case, right? So we have stochastic forcing, goes into our black box model, many realizations or many output results. If you have stochastic forcing, you have to aggregate those to probabilistic results. It's kind of like the basic rule of modeling, stochastic in, probabilistic out. Just like when you're doing calibration, observed in, discrete out, that's compared to observed simulation results. What's really important when you have stochastic forcing, you'll spend a lot of time, generating your cone of uncertainty, your description of uncertainty for what your inputs are. And that's great, and a lot of people spend a lot of time on their model. Most important thing for probabilistic simulation is sampling. If you don't sample your description of what your events are, or your uncertainties are, you will bias all your results much more than whatever you do here or whatever you do there. So fortunately, with modeling and uncertainty, there are a whole bunch of tools available now. Lots of great tool sets. We saw data assimilation on the calibration slide. That, of course, works with exact value uncertainty. There's also post-calibration sensitivity analyses in the ASTM sense, also exact value uncertainty. But when you're doing stochastic modeling, working with the unknown unknowns, there's pretty much just dumb Monte Carlo analysis. You need to make sure you sample all of your possibilities robustly so that when you get to the end of all those calculations, you have an output cone of uncertainty that makes sense. Sorry about that. All right, so probabilistic risk assessment, or PRA, is a framework that explicitly incorporates what-if scenarios with models into a formalized experimental design. It is Monte Carlo-based. NRC performance assessments are one sort of highly constrained example of these. But what happens in a PRA is your experiment is represented with trees. These can be event, fault, or decision trees. Each time there's a branch, an event either occurs, a decision is made, or a failure occurs. Okay? And a probability distribution is used to make that decision, determine if that event occurs, or determine if something fails. And it's just like you rolling the dice each time. Depending on what numbers come up on the dice, that's what decisions make. Okay? So, PRA, it's a very common sense approach. It's been widely used. Actually, many important parts of it were developed just up the road here for NASA. The goal of PRA is always to support resource allocation and decision support and planning from a risk point of view. It requires a comprehensive scenario set, so you're interested in catastrophic failure, as well as a sequence of seemingly insignificant events that lead to serious problems. So, and it always requires a realistic assessment of system performance. It's not a design basis thing. You're not going to say, how well could this work under ideal conditions? It's how well is it going to work every day? Are we going to kill the astronaut? That's what you're trying to figure out. So, if you looked at a historical progression of getting to PRA in terms of, analysis types, you start out with being a bookie. The world's second oldest profession, setting the odds. Then you have engineering reliability analysis, and that eventually evolved into PRA. So, setting the line or setting the odds is a very useful analogy when thinking about setting up a PRA. It's also very useful when you're looking at future what-if scenarios. So the goal is to have a plan based on risk assessment for every important scenario. You're not just making a single bet on a single future. You're not letting all the money ride on black. You're actually setting the book. So, future scenarios within PRA are explicitly defined. And so the scenario is essentially the tree. So to have different scenarios, you have to have different trees. Different trees are composed of different decisions, events, faults, things like that. The only other way you could have a different scenario, or the way you could have a different scenario with the same tree, would be a different probability distribution for one branch, or one or more branches within the tree. Okay. So, future uncertainty when you're using ensembles. So the purpose of ensembles in terms of probabilistic modeling is to provide the probability distribution that you're going to sample for every force event. Okay. And this is the part where it's really important on how you sample this. Bottom, the scary sampling. You can see it's actually the same blue line, both charts. It's just this one looks so much smaller because it's showing all the bias that's introduced by inappropriate sampling. Right? That bias will propagate through your model to your results, give you a scary potato head result. Right? So you always want to make sure your sampling is reproducing your probability distributions, at least approximately. All right, so that kind of covers the background information. So now we move on to the case study. So a little bit of information about the case study. It was an applied research project. It's wrapped up a while ago, several years ago. Because it was applied research, the goal was to look at methods, algorithms, and approaches related to PRA. It wasn't to look at the specific site. We had to choose a site to get the data sets to make the analysis. All right? But the overall goal, quantify future risk and impacts to water resources, and climate change, and land use and land cover change using PRA. And as we set up this problem, which is kind of hypothetical, we chose water availability as our metric. And we defined water availability as a combination of simulated contributions to subsurface water storage and stream flow generation. Right? So water availability conceptually represents what's available for management and stewardship outside of the watershed. One limitation I'll say up front, we don't have this phrased in terms of costs. We'll see as we go through this example how important that becomes, but our metric evaluation is subjective, right? We just chose to say that a physical process outcome, if it's more, is better, right? That's subjective. All right, sorry. The study site was the Dolan Creek watershed. That's about 100 miles mostly west of here. The important thing to notice with these initial maps is how much green there is as compared to how much blue. So the green and the blue are hydrologic soil groups as you probably mostly know, the green means no infiltration, all runoff. The blue means high infiltration, no runoff. Sorry, the green means all runoff, high runoff, no infiltration. Blue, no runoff, high infiltration, for the most part. And so,
Hang on just a second, sorry.
Sure, no problem. So when that comes back up, the blue is mostly in the stream valleys. It's a karst terrain area. It's drip communication between the surface water and the ground.
What's the risk of that happening?
Always pretty high. So back to a little bit more of the details. Site-specific water availability. Just had two components to that. Stream flow generation. Stream flow is generated at the first order by increase in precipitation intensity. Decrease in precipitation intensity will make for less stream flow generation. And then for subsurface water storage, the second component, we broke that into two categories, somewhat based on the models we were using. But we have category A, deep percolation through soils, which is a diffuse process. And then category B, stream seepage losses, direct communication from the streams to the subsurface. And that's more of a focus process. So in terms of the subsurface storage component part of water availability, component A, deep percolation out of the bottom of the soil column. Where infiltration cannot occur, you cannot get deep percolation, first of all. And then the second thing is, this is the mechanism within our analysis for water availability that's subject to temperature change. So temperature change typically increases potential evapotranspiration, PET. And if PET increases, then potentially the amount of deep percolation can be reduced because the plants are using that water going through the soil column. For component B, the stream seepage losses, again, increase in precipitation intensity is the first order driver, so not really that dependent on temperature change. Sure, there's some dependence there, but we're just talking, first order here. All right, so we developed a dynamic PRA framework that uses multiple models and then explicitly tests hypotheses. You'll notice that there are two pathways, an null hypothesis and an alternative hypothesis pathway. Each pathway contains two models, a water balance model and then a weather type representation. And this is the only place I'm going to show it, but we're showing a little bit the temperature increases, and so PET is expected to increase consistently with consistent temperature increase. Oh, and for our results, there are probabilistic differences between the pathways. So we're looking at what is the change in magnitude and likelihood of change in magnitude of water availability. So when we compare observed to projected, the null hypothesis pathway represents historical conditions. Okay. The alternative hypothesis pathway represents our projected future. For this, there's two different projected futures we're looking at. First is climate change. A while ago, we just used an ensemble CMIP-5 model simulation results from two emissions scenarios that provide our description of that. Land use, land cover change was the second thing we looked at. In that, we ended up deriving a simple economic development model that came out with change in impervious area over time as our land use change. So, in terms of our stochastic forcing, going into the probabilistic simulation, what did those climate model results say for the site in general? About a 3 degrees C average temperature increase, and on the annual and seasonal basis, we showed very little change in expected precipitation in the future. All right. So this shows the current and future Copenhagen climate classifications for the study area. This was done by others from these same model simulation results. Unfortunately, and this speaks to poor choice of study site, but what ended up happening is we didn't figure this out until after we already had the money and it already started. But there was no change in climate classification, which kind of threw a wrench in our land use, land cover change analysis plans, and that's why we had to fall back on the change in impervious area. So what is it? It's semi-arid present day, semi-arid projected future. You don't see any other classifications anywhere near the study site. Semi-arid for our purposes means that actual evapotranspiration, AET, is limited by water supply, right? We know we have plenty of PET because temperature's going up and it's a hot area and it's a dry area. And so the PET is always going to exceed the water supply. AET only is water supply limited, right? We also just saw that we're not expecting precipitation to change on sort of an annual average basis. So, might mean our results are kind of boring. So PRA, uncertainty and realistic assessments. It's the key. You want to realistically assess system performance as part of this. And when we look at the uncertainty, we have uncertainty related to model inputs and to model results. So for the input uncertainty, we have those climate projections which we're using as inputs. We're just taking what's givens. How good are they? We'll talk about that a little bit. And then for model uncertainty, we know that all models are wrong, and some models are useful. But what you need to do for actually applying a model in this framework, we just need to focus on where the model is going to be useful and focus our analysis on that. So the climate model uncertainty. Climate is long-term average weather. The water balance models that we use weather forcing as input, not climate. WMO, I think, currently projects that the best numerical weather prediction models will be able to accurately predict weather forecasts up to 15 days in the future by the 2050s. And there's some thought that maybe, I'm sure knows better about this than I do. This isn't my field, but the 15-day accuracy threshold is a physics-based limitation that may not be able to be surmounted. Currently, the best numerical weather prediction models are accurate out to about 5 days. Global climate models are reduced, less accurate versions of numerical weather prediction models. So we're not really expecting them to predict accurate day-to-day weather, right? They do provide stochastic weather forcing, and that when you average them over long term, they provide a good description of expected future climate. So what we're saying is the global climate models do a good job of representing that random process that generates stochastic weather, and it tells you what that random process is and how it works. Okay? The global climate models are good for differences in climate normals, mapping of climate zones, things that are working on a pretty long-term average. They're not going to predict individual events, so just that's kind of what we're stuck with. The water budget model that we use. Thank you, Sam, for introducing HSPF. We just use that because we happen to have a copy lying around that we can modify. Had to modify it to do the land use, land cover change simulations, as well as the clients. HSPF can be useful in our case for calculating monthly average discharges, given weather force input daily weather force. HSPF doesn't have hydrodynamics. It can't, if you tell it, how much water is coming into someplace, it can't decide which direction the water goes, right? The analyst always tells it where the water goes and how fast it goes. All right, And so when we present the results for PRA, again, we know we have the stochastic weather, so we're not going to provide predictions for, an extremely wet June of 2054 or anything like that. We enforced weak stationarity across 30-year intervals, just so that our inputs, we would get a fixed distribution for our input forcing that would have the same probability for exceptionally wet and exceptionally dry conditions for every year within there. All right. Then we arbitrarily added in some possibility of additional precipitation intensity into our thing. We said that this was as, more extreme 100-year events is kind of how we put it in there. We didn't probably put it in there in the best way, but it's in there. And our support for that is, there is some expectation that increase in average temperature will provide for increased precipitation intensity at some points, air will hold more moisture in the future. And eventually you could have, more intense and frequent storms. All right. So we provided our results in terms of differences between the pathways and probabilistic differences. We did that because it's a very data limited site. No realistic possibility of a good calibration. And what you can see for the results, really what came out is that the only real change came from those arbitrary 100-year, this extra increased precipitation intensity things that we put in there, right? So if you look at AET, it's pretty much the same. Again, remember AET is supply unlimited, PET is strictly temperature dependent. And so we just have a little tick up there as we get in those, bigger, more intense, more infrequent extreme events as simulation time goes on. Same thing shows up for runoff and for contributions to subsurface storage. Again, it's all driven by the event intensity increase because the contributions to subsurface storage are almost all focused recharge in this case because of the configuration of the site. So that was the climate change what-if hypothesis test. For the land use and land cover change, we get a 10% increase in impervious area for the first now future projection interval, and an additional 10% increase for the second future projection interval. This is cumulative water availability, and you can just see the blue dotted and solid lines, represent the median and average land cover change scenario. And you can just see a slight increase in the slope of that line, so more water availability as we go through those future periods where we have increased the impervious area. Okay? So increase in impervious area directly acts to increase surface runoff in this model approach, the way we set it up. And so that increase in stream flow also directly increases the possibility for seepage, stream seepage to subsurface storage, also based on the way we set this approach up. So that was our case study. And as I said, it's been a while, and as we went through it, we knew there were certain things that we would want to change. And so we'll talk about updating the line now, which is what would we change, or what should we change now that we've been through this analysis. So, thing to keep in mind is with the scientific method and with setting odds in general, it doesn't ever stop, right? Just there's an innumerable number of hypotheses to test. You don't ever get conclusive proof of a hypothesis usually. So just, try one thing, see what you learn, and try the next thing. Okay. So the shortcomings of this analysis, probably the biggest one, we didn't do any cost-benefit analysis. Okay. So what we came out with, we had our metric of water availability, and we came out that increased water availability from increased runoff was a good thing. So if we had costs in there for the various things that go into that, we might have a different result, right? And then we had two assumptions that are kind of shortcomings. First assumption, we assumed that increase in large event intensity with no corresponding increase in drought conditions. Intensity or magnitude, right? So introduce bias right there. Second thing, we assume that more stream flow means more stream seepage loss. It's enforced by both the shortcomings of HSBF model and how we set the model up. So for our possible change one, we could increase the dry extremes in our representation. Two box and whisker plots here are actually from a different presentation, different study, but they make my point. This one would be the one with the increased dry extremes along with increased wet extremes. You can see the average, which is the green triangles, stays the same, but we have a whole bunch more really bad precipitation events, really high intensity, high magnitude precipitation events, and we have a whole lot more dry period, right? The 25th percentile portion of the box is shifted way down, the lower whisker is shifted down to 0. Right? Much drier. Median moves down too. So that would be one way to address, rebalance our representation of the climate change. The other possible change that we could do would be to isolate the seepage losses to a particular bandwidth of discharges. And in this case, what we would probably do is we would say that seepage loss can only occur in normal and low flow regimes. So this example is also from a different study, but it shows Blanco River recharge zone flow duration curves across the Edwards recharge zone. The very unique thing about this plot is the upstream measurement in the normal and low flows is a darker blue line, and it plots significantly above downstream measurement. The integration of the area between those two lines would, of course, be total seepage loss. The other thing to notice is that once we get into the higher flow regimes, and especially the out-of-bank high flow regimes, it flips back to the expected approach, right? It flips back to the downstream measurement being more than the upstream measurement, which is what you would expect under normal conditions with no losses. All right. That's it for my talk. Thank you, guys. Thank you for having me.
Any questions for Nick? Well, I know I have a couple to start with. Sure. So, one of the concerns that we've talked about before is how do we appropriately pick or represent, either stochastically or some other way, these infrequent weather events. We kind of know what the trends are based on the climate modeling, and we kind of have a current record of those events. But again, as we talked about before, we know climate is changing. So trying to even picking the last 20 years based on even the Const data suggests that may not even be representative. How do we not only represent those infrequent events in terms of how to understand what the effect is on the system, but then also how do we do it in a way that is realistic enough to convince people that that analysis is appropriate?
Okay.
I'm sorry, it's a big question.
No, it's actually a very good question. So I would say the first part of it is just to be realistic and common sense about it. So when you're looking at how do we need to convince people to do this, make sure that whoever it is you're convincing, that's what you really need to look at. Like most of the time on future scenario type decision making, you're looking at, some sort of metric that's between the 10th and 90th percentile, right? So it's not on the tails. It's not the drought record. So, you want to make sure you need to know that for whoever the decision makers are, first of all, so that you don't do basically a whole bunch of, it's not impossible work, but it's always going to be highly uncertain, right? Like that's where the uncertainty is going to be the worst, is once you get out into the details. Right? And so if you do need to go out to the details, then you probably want to look at maybe different models, different things like that. I know from what little I know about weather attribution studies, and you probably know quite a bit more about this than I do, like they tend to look at a variety of ensembles and different types of models to do it. They look at like sea surface temperature to make sure they're, I guess, probably getting El Niño. And they also look at like the regional high resolution geophysical models, and they also, CMIP models, all of that stuff. And so, it comes back to the thing of make sure you're basing it off the right models, right? If you need to look at something in the tails, you need to make sure you're using models for your projections that can do the tails.
Yeah, okay. So I have one follow-up question. So as you've heard today, we're kind of a small regional agency, so we have kind of this limited number of models that we can apply. And so, I'd love to have a beautiful stochastic analysis that offers a range of outputs so we can say, here's a median value and we have a 90 percentile chance of exceeding this value of low stream flow or something to that effect. But as we found out, the HSPF models that were developed are quite complex. So you end up having to run multiple models in one stream basin, and the chance of being able, and we've perceived this as like trying to run those models becomes so computationally intensive. We don't really have that. How do we address that?
My personal approach is just make the statistics you want synthetically. You can do it from one model run, you can do it with a weather generator, there's all sorts of statistical techniques out there. Just make the time series that you want that has the statistical properties that you want for the forcing, rather than relying on a model. So, you could probably just cut to the chase and make something synthetic up, and if you really needed to look at the end of the world, then, make something that looks like the end of the world.
So something as simple as recharge distribution for each basin that we just sample appropriately.
Sample appropriately and make it so, you need to then, there's all sorts of statistical ways you can fill out your distribution,
Sure.
right? Like you could just get one model, and you could bootstrap it or something to make a nice
Very, very interesting. That's good.
distribution.
I know we had another question down.
Yes,
The microphone's coming.
This question isn't specific to your talk, but I've had a question about the influence of the urban heat island effect on climate models, and I wonder if sampling is skewed because of maybe sampling in metropolitan areas, and I've seen San Antonio totally change growing up here, and I've always...
I'm going to try to defer to somebody else on this, because it's not my expertise, but do you have any insights into that? Sorry. It might not be yours either, so I don't mean to throw you off.
I do know some of that, yeah.
It's good.
Yeah.
I was gonna say, make that nice for our wonderful videographer. So yes, on that question, the global models do incorporate changes in land surface, land use and land cover. Actually, more so now, and that's through the land surface modeling site component in there. So there are ways that go into incorporating the urban heat island effect and how that's changed over time. So the other thing I can add to that is that it's come up a lot more so in the last few years, in particular. So a lot of the newer generation models incorporate that in as a part of their activities, along with the rural land use and land cover. As to the sampling for observations, you were getting at too. There is some of that, but a lot of the different monitoring centers and groups in NOAA is very mindful of this, recognize that we can't actually just look at what's going on in an urban environment because of that effect, actually. So there's a lot of focus on rural stations. There's also a lot of additional analysis that was done in the sense of basically, if the city hadn't built up there, what would the temperature profile of the city look like? Before you define what observed temperatures are there and then aggregate that to the global change. So, long way to answer your question, but the short answer is yes.
Any other questions?
Yes.
Okay.
I'm a little bit confused. So this study that you're referencing in Verde County, you're looking at groundwater availability, that groundwater that might be available.
No, and just water availability. And
Water
we define that purely as if it wasn't, if it was a porous medium environment, what you would call recharge, plus stream flow runoff.
Okay, and so the increases in impervious cover that you're looking at, what would those be coming from?
So it's not a very developed site, and we didn't get any significant change in land cover from our analyses by other people of these climate results. So we were kind of struggling for something to do. And so basically, we somewhat just decided to do a 10% increase in impervious area. The only real economic driver in that area would be more drill pads.
Oh, so it would be for
Development. Yeah,
Pardon me?
economic development.
economic development.
Yeah.
So then I'm a little confused because if you have increased impervious cover from economic development, we'd also have increased pumping.
Yeah, but we didn't look at groundwater at all. We cut this up at the bottom of the watershed. Right, so there's no groundwater in this study. Sorry.
Yeah, I mean, that's a good point in terms of the Edwards system.
No,
You know, there's potential for increased runoff with impervious cover. Could have a big significant water quality issue, but actually could add water to the streams to do that. But then you also have the other factors that you mentioned that are associated with the impervious cover, type of development, water use, other stressors. And so I think, Nick was kind of doing this probabilistic analysis to help do that, so that was kind of arbitrary in terms of how they defined it out there. But I think it's kind of a good example of the impact of impervious cover to that runoff. It's got a good example of what you might expect.
that's why you always need to use cost.
Yep.
Because then you can easily factor in things like degradation of water quality, landscape changes, change in land price.
Any other questions?
Just a quick one. Were you able to associate any p-values with the hypothesis that you showed?
We did.
Well, thank you again, Nick.